So you can see that we can turn um, the numbers in the file and have them linked to the other txt files.
Of course.
So also to prevent data leakage, we have to divide them one by one, or else the model will cheat.
Correct.
So we train the model by person, and they are 21, 3, 6 for the train, veil, and test sets. We also choose a seed as 42. And for the last part, we develop a parametric windowing engine. So the window size is 128 samples and a 50% overlapping using dynamic stride calculation. Also, because we will use tau in future experiments, so we already implement it here. Okay, so
my part is task 1. Next page. For a setup, the data set is the same as described earlier. Across every experiment in the test, we keep the training pipeline fixed, add an optimizer, learning rate of 1e minus 3, dash size 684, up to 25 epochs with early starting, and C42. The baseline encoder is a single layer GRU with 64 hidden units, around 13.6K parameters. Next page. For a baseline at the conventional 2.56 second window, our baseline GRU achieves a test accuracy of 0.93 and a macro F1 of 0.726.
So what is the model here? Which is that? What model do you have for the baseline? Is that just the
GRU?
I see. So why do you call it baseline? Okay, I guess. Okay, so this is just a GRU. Okay.
Yes.
Just let me think. Let me parse. Can you close the meet window? Gensai, blah blah blah. Yeah, close. Yeah, good. Training windows. So the stride is there, right? So again, what's the S for the stride? Remind me, what's the stride length? Can you go back to the formula of the stride length? Let me think. Go back. This one here. So you have a dynamic stride, right? So the window is omega. And 1 minus overlap. How do you choose the overlap? Then can you go to that slide and tell me how you choose the overlap? Go. Go to the current slide. Forward. This one here. How do you choose the overlap? Yeah, so the omega is 2.9 seconds. The tau is equal to 0. The peak is that omega. How do you choose the overlap here? 50%. Did I read some? Yeah, 50% overlap, correct? It was in the previous slide. Go to the previous slide. Next, just one slide. Go forward. There was a 50% here. What is the overlap written here? No, what is the... Okay, go to the next slide. What's the overlap? What's the overlap here? What's the overlap? Ayo. Yeah. Can you answer? Tinodoma. Very simple question, right? Hello. 学生，你在吗？ Hello. Simple question, guys. I just want to know what is the overlap. Guys, can somebody answer something? Are we okay? Is somebody died? Is everything fine? Should we take a break? Somebody tell me what is happening. Guys, what is happening?
I will text the I don't know what's happening, so let me check. So,
Yeah, I don't know. I just that's a simple question, guys. I didn't want to create. Yeah, just because I'm thinking like how many. If I'm thinking this right, because I want to know how many instances of inference you have, right? Because the more overlap you have, the more windows you can fit. So when I want to compare. So you understand the issue, right? So as the window length gets longer, then you're doing fewer estimation rounds, right? So if the window length is 10 versus 5, right? You're doing double the estimation. And I want to know the overlap so that I can roughly calculate if the number of prediction as the window change is comparable or not, right? Because if the overlap is 0, then of course, as I double the length, I have half of the estimation instances. So I'm just thinking about that. That's what I wanted to know. Because if you, for example, if the overlap is only always on one sample, right? Then you can have the same number of estimation instances as the window changes. So I'm thinking about what is the variance in the prediction. But well, it seems we'll never know the answer to this. Okay, guys, please, let's go ahead. I cannot be here all day. I try to entertain myself, guys, but there's only so much I can do.
where is it?
Can we go ahead, Group A, or?
少安，你还在吗？
我觉得他在啊。
是，对啊，我们现在是谁在讲？OK，那我们继续。
OK，准备好了吗？ Guys, let's go, please. We all have stuff to do in life. Guys, should we go to the next group, or what should we do, guys?
Oh shoot! Sorry. I didn't share my screen. Sorry. Oh.
Okay, so do we have the answer to the question, or we just go ahead and we pretend it never happened? Okay, let's pretend it never happened. Okay, let's go ahead.
Uh,
You have to close the window. Yeah, close the window. Yeah, go ahead. Can somebody go ahead?
overlap is
Oh, okay.
0.5.
It was written somewhere and I didn't see it. Okay, go ahead. Can we go ahead, guys?
Is
Go.
应该是前面还没讲完。
All right.
Okay, go ahead, guys. Overlap 50%, and that's the difference in the window size. Go ahead, guys.
Okay. Based on the gap between test accuracy and macro F1 is not worth nothing. The 6 postural transition classes each only account for a small fraction of the data set. So they pull down macro F1 while leaving the overall accuracy high. For this reason, we focus on macro F1 from here on.
Okay.
Now look at the window length sweep. The pattern is non-monotonic, and the conventional 2.56 second window is not the best choice.
Yeah,
F1 peaks at W equal to 1 second with 0.784, and W equal 5 seconds also outperform.
But this is related to the question that I asked you, right? Because you have fewer and fewer samples as the window becomes larger, so you have fewer learning instances, right? So that's why you see the decrease, right? So it's not that I think it's not that the model is so the prediction would be better, but you have fewer instances, so you have less learning to do. Go ahead.
Okay, that's the W equal 10 second
Okay.
value of 刚刚没讲，
这样，抱歉，现在哪一页
这页还讲好。
？OK，抱歉。
The W equal to 10 seconds value of 0.929 is suspicious. It only had 1,200 training windows, and F1 actually exceeds accuracy, which is a mathematical giveaway for small sample noise.
Correct. Go ahead.
可以下一页。Next, we evaluate the prediction horizon. Right.
Go ahead. What is happening today, guys? Why are we taking forever to do this?
我的简报好像被删掉，还是很少的一页？
你是说这页还是说？
不是，就是刚那页跟这页中间应该还有一页。
哎，我应该是没动到，不过还是你先继续讲。
哦，好，我直接从这页开始。
Guys, it's your presentation, right, guys? Just don't.
Oh, sorry.
Forward, right? What are we doing here? We're just waiting for you guys to understand which slide you put where.
I think there is a slide. The page is deleted by someone.
You have to roll with the punches, right? So if you present to your boss and you stop the presentation because there is a slide that you don't know, then you're not gonna have your job for long, right? So go ahead. Take it in stride. Be brave. Improvise. Go ahead.
For a missing data experiment, we compare 3 perturbation patterns at a fixed window of W equal to 100 to 28.
128. Okay.
As
Samples.
shown in the bar chart.
Yeah.
Here is a clear ordering. Channel dropout is by far the most damaging. Block dropout sits in the middle, and random point dropout is essentially harmless. The first surprise is that line point dropout actually improves performance.
Right. It's nice. Yes.
At p equal to 0.1, the macro f1 jumps from 0.726 to 0.805, which suggests the clean baseline was slightly overfitting and
Yep.
benefits from input level regularization. The second key result is on the right side of the chart. Dropping all three as the thermometer channels collapse F1 to 0.531. While dropping all three gyroscope channels only reduced it to 0.677. The accelerometer is the dominant modality for this task,
Okay.
and the gyroscope cannot fully compensate for its loss.
Yeah. You understand what is the gyroscope, right? The gyroscope versus the accelerometer, right? So the gyroscope gives you direction information. So I wonder. Yeah. Okay, go ahead.
Next page.
I see. Okay, go ahead.
Now the model comparison at the conventional window. We train 6 architectures using the same training pipeline. CNN1D wins over O with macro F1 of 0.856. These matches are architectural intuition. Local pattern detectors operating across multiple sequence positions capture brief, discriminative motion motifs. The standout surprise here is the logistic regression on per channel mean and standard deviation. With only 156 parameters, it achieved F1 of 0.805, beating GRU, LSTN, and TCN.
And it's much faster as well, right? The latency is 0, basically. Yeah.
This suggests that at a 2.56-second window, a large part of the discriminative signal lives in low-order statics rather than in long-term temporal dependencies. Capacity is not the bottleneck here. However, this finding depends on window length. So let me show what happened at W equal to 50. Next page.
Exactly, right? Because the window length, it's only 2 seconds, right? So, okay, tell me about this.
因为上一页还没讲。
抱歉。
谢谢。To meet the project requirement of comparing models across at least 2 window lengths, we evaluated the same 6 architecture at W equal to 50, which corresponds to the 1 second window. That was the best choice in the earlier sweep. 3 observations and out. First, the race is much tighter here. CNN1D still leads, the margin over GRU and LSTM both at 0.784 is very small. Notice that the recurrent models actually perform better at this shorter window than they did at W equal to 128 in our single seed run. Second, the simple model surprise vanishes. Logistic regression drops sharply from 0.805 to 0.713. Handcrafted mean and STD features need a longer window to be informative. Over only 50 samples, the statistics are too noisy to discriminate 12 activities well. Third, this confirms that the takeaway on the previous slide is window dependent, not a universal rule. Next page.
Okay.
To wrap up, these scatter plot maps are complete experimental metrics. The x-axis is parameter count on a long scale. The y-axis is test macro F1 with blue dots for W equal to 50, orange dots for W equal to 128.
28. Yep.
First, point parameters does not mean better F1. CNN 1D dominates with only 12,000 parameters, while the 68,000 parameter tiny transformer never catches us at either window scale. Second, window selection is primary design choice. The same model can swing by 0.1 to 0.2 in F1 just by changing W, as seen most clearly in a logistic regression. Third, the best configuration in our experiment is CNN 1D at W equal to 128, reaching macro F1 of 0.856, clearly above any sequence model. If we had to deploy one configuration from this study, that would be the best choice.
Very good. Very good. Okay, go ahead.
Next page.
应该差不多。
好。
Okay, moving on to text 2. The course objective of this phase is to evaluate the consistency of subject level representations. Essentially, we want to address the fundamental question: do the micro climatic features learned automatically by the deep learning network group our 30 subjects in the same ways as human-defined macro activity statistics? So to explore this, we construct two entirely independent vector spaces, a sensor drive view and a level drive view, and contrast their clustering behaviors. Okay, next page. So I'm introducing the metrics over here, the ARI and MNI. ARI means that when we clustering two groups, we use this index to represent how close this two different clustering is. So if the ARI is very high, this two kind of partitioning is very, very identical. And NNI means how much information can be represented by the group method. Like like it qualify how much information we get about the clustering space. Okay. We use the Silhouette analysis to
Silhouette, French people.
Silhouette.
Well, if there is a French word, it means that you can throw away 50% of the letters and the pronunciation doesn't change. Okay, think about croissant, or think about whatever. So just silhouette, yeah. The Italians always make fun of the French, because we are a superior race. No, I'm joking, but the Italians are always shitty on the French. So silhouette, go ahead.
Okay. So we use the silhouette analysis to find the K for the
You have to choose the K, right? You have to
a
choose the
sensor
number of
drive level and level drive, like this two. So for the sensor drive, we pick the 6, K for 6, and for the level drive, we pick 4. Okay. And
But there's not much difference for the sensor, right? Interesting. It's very interesting. Go ahead. Very nice.
Okay, and we can see the ARI is very low. It's only 0.056. It's very close to 0.0 and very far away from 1.0. So these two type of the clustering method are very, very different. Yeah, and then is 0.2 is not a big number. Okay, next page. Okay, and then we do the dimensionality reduction and visualization through the PCA and TISNI. And TISNI can capture the.
Can you give me a second? Give me a second. Let me, because there's a lot of info here. So this is the sensor derived, label derived, sensor derived. So you have the sensor derived twice. Good. Then we have the 5 clusters for the sensors and the 6 clusters for the sensor and the 4 clusters for the labels.
Yes.
And then what is the difference between the first sensor and the last sensor?
I use TISNI and PCA.
You're right. Okay, go ahead.
Yeah.
So you don't have PCA for the label derived. Okay, go ahead. I passed the. Go ahead.
Okay, and then we can see from the sensor drive, if we use TISNI, is the point spread more wide and wider, and for when we use PCA, it's like have more overlaps over here in the left part. So it's basically because like TISNI can capture like some nonlinear features, but like PCA can capture linear more. Then maybe the features are mostly nonlinear. So when we visualize this, you have more overlap over here.
Let me correct you. I think you want to say non-linear dependencies versus linear dependency. So PCA captures linear dependency and TSNE non-linear dependency. Go ahead.
Okay. Okay. Next page. And we want to know if we force the label, the sensor drive and the label drive to the same K, what's their ARI score in this scenario? So if we force them to the K equals 3, the ARI is not only like the very small number, is a negative. So it's basically not like very non-relevant. And so we can see when we force the K to 5, it have the biggest ARI, but it's still not a big number compared to 1. So we can see like the sensor drive features and the label drive features are very different. And we can have a takeaway like in the choice of cluster K is not just a hyperparameter, like it completely dedicate whether the model captures shared or entirely orthogonal dimensions of human behaviors. Next page. Then we further suggest test the geometric robustness of our feature space. So we test the clustering algorithm sensitivity. We have like k-means versus agglomerative. Then it have ARI equals to 0.6 is a fairly high score. So it shows us a high stability over the algorithm sensitive. And for the pooling layer sensitivity, which is min pooling and max pooling, and the ARI score is 0.2. It's fairly a low number. So it can be seen that like the choice of the pooling method can affect the clustering results a lot. Okay, then okay, I think I can go to the next page.
No, tell us about go back. Tell us this one here. The image is very nice, right? So tell us about the image here. Yeah. So that
I think I will go detail on this image because I have this image in later. Yeah.
Go ahead. Just I like it. Yeah, that's I wanted to know more about it. Go ahead.
Okay, next page. Okay, and we wanna find out is there any outlier over here, and we define our anomaly threshold as mean plus 2 standard derivative and deviation, sorry. Then the final count is 0. I think basically because we use the the best k for this two clustering.
So because in the sensor space, so the k was smaller, right? The k was 6 for the sensor one, right?
Yeah, and there's only 30 volunteers in this set. So it is. I think it's because when there's some outliers, but I have too many clusters, so they like just have a special group for these outliers.
I understand. So you think that one of the features correspond to the outliers. That's why you have 0 outliers. So tell me about the image. So in the image we have the subject ID, and then we have the distance between the cluster and the centroid. I see.
Yes.
And what do you have some zero? Oh, because you have some 0 distances because why do you have some 0 distances? Why do you have 2 people that have 0 distance from the centroid? Seems to be some missing data or something in the pipeline that went wrong, right? You shouldn't have 0 distance, right?
Yeah, that's weird.
Because if you were like k-matoids or something, then maybe it could be that your algorithm chooses one representative. But this is k-means, right? So
maybe I can double check.
Can I give you the explanation? You have 6 clusters, right?
Yes.
So 2 clusters contain only one individual. That's my
yeah. That makes sense. Yes. And maybe we can go back to the Disney.
Exactly.
Go 前页，
这不是前页吗？
在前页，对。
哦，拍摄。
But also here you see it, right? Because you see that there are 2 columns that correspond to 0 individuals, right? So
yeah.
Go ahead.
Okay. Then I just keep going. 好，那就继续往后好了。
Okay.
再下一页。OK， 这页。OK. So 对 Q1. Okay. So the first question of this text, like, do sensor drive and label drive embedding produce similar subject clusters? And the finding is that no, they produce fundamentally distinct clustering and with negligible overlap. Like as we shown on the result, we choose K for sensors 6 and K label 4. The ARI score is only 0.056. So they are fundamentally distinct. Okay, and we force the alignments like for have best result k equals to 5 is only 0.13, so it's also very small. Okay, next page.
Nice.
What's qualitative pattern emerge when
There are two pronunciations. One is qualitative and the other one is qualitative. So you can choose the one that you like.
Okay, what
Choose the one that
qualitative
you like.
pattern emerge when visualizing the embeddings? So I'll go detail on this chart. Like in cluster 0, we can see the red means the value is fairly high. So we can see the frag act 1 and dynamic and static ratio are fairly high. We can see I named this group as the high intensity walkers because the frag act is called walk, and they walk for a while and stop and walk for a while. So this kind of people will get grouped in the cluster 0. Okay, and cluster 1, we can see the frag act 5 is have the highest. It is standing. So there basically the standard. There's standard, and sometimes they just stand there, and sometimes do the frag at 4 and 6, which is lying and sit. So they just don't move and just stand, sit, and lie. Okay, and for cluster 2, they're liars because they have the highest frag at 6, which is lying. So in the test, it's always lying that right there.
Can I point out the spelling mistake, which is maybe indicative of or something more? You know, to lie and to lie, they're the same pronunciation, but two different words. So are they liars or are they liars? You know what I mean?
Oh, yeah. I misspelled that.
Wait, let me see. What do you have? What is the CAD program that you have open there? What is the CAD program? Let me see. I saw it. Go back. I saw a CAD program. Let me see the CAD program. I saw a 3D model. What was the 3D model? Go back.
What?
I saw a 3D model. Show me the 3D model. Yeah, Studio. Let me see that one. Let me see the 3D model.
We can do that after
Oh, damn it.
Yeah,
go ahead.
Later.
I really like CADing, guys. So that's my pastime is CADing. Go ahead. So then you have the sitters that are there. So no, stay on this one here. Do you know how many people were in each of the clusters?
How many people?
Yeah, just roughly, right?
I think
you have 11 people, right?
Yeah, I think I should know, but I gotta check.
Just wondering. And then the question is that which one are you? Hopefully you're not a liar.
Trust me, I think I'm in the sitter because I always did in front of my computer.
That was my guess as well. You know that we are mostly sitters in the class, okay? Not you in specific, but mostly in the class.
Yeah.
Very nice.
All right. Okay. So the level drive space, the result is right here, and for sensor drive space k equal to 6, since the ARI between the label and the sensor is almost 0. So my guess is the sensor drive, they maybe capture their like stride power or like gate rhythm or device mounting tolerance. So they capture like very different signals from that person.
You're right. Yeah, because the way the sensor is mounted probably changes the data a lot, right?
Yes. Okay. Next page.
Yeah, you know what? I was wondering if the cluster also will reveal male and female, because I assume they have again, guys. When we talk about male and female, I have to be careful. But I assume they have different average weight and average height. So I was wondering if the activity will also depend. You know, it was a way to determine the gender by the activity, but it seems that from the clustering you don't see it, right? Okay, go ahead. Yeah.
Okay. And the question 3 is how sensitive are the cluster results to the choice of pooling method, distance metrics, or clustering algorithm? And I have shown the ARI score before. Like for the clustering algorithm, sensitivity is very stable. And for pooling method, sensitivity is very extremely sensitive. Okay. Main pooling capture the subject's normative baseline behavior, whereas the max pooling selectively isolates peak kinetic shock vectors. So it changes the user's identity.
Yeah, that's a little bit of a guess, right? So it's
Yes.
yeah. I mean, of course, you have to spend more time on the data to understand it. Okay, go ahead. Very nice. Very nice. Very nice, guys.
Okay. The last question is, are there subjects that consistently form their own cluster or behave as outliers? We have 0 outliers. And I think basically because the k equal to 6, so we have some outliers maybe got cluster in a group, so no outliers detected, because maybe also because we have only a small pool of 30 subjects.
Of course.
Okay. Okay. I think that the end. Okay, next page.
Let's see. This one here, I'm curious to see how it
Hi,
goes.
hi
Hi.
everyone. Today I'll be presenting task 3, where we shift our focus on offline classification to online activity detection. Specifically, we built with a model that outputs a blank class to remain silent when it isn't confident yet. Okay, next page. Next
No,
page.
let me pass a second. Let me pass. So this one here, you keep the window of 2 seconds, right? And the grace, what is the grace period tau here? What is the grace period? Tell me about the grace period.
The grace period is 32 frames. Mean the model is forced to output blank
Right.
for the first 0.64 seconds. For the architecture, we use a unidirectional GIF. It's crucial that we strip away any bidirectional layers to ensure the model strictly respects causality. Okay, next page.
Very good.
Next. So,
Get it upset. You have to get it upset. Go ahead. Very nice.
the line self point RNN equals in that GRU is the soul of our causal model implementation. We intentionally omit the bidirectional equals true parameter. It ensures our GRU operates directionally. Okay, next page. To prevent the system from guessing randomly when information is insufficient, we defined num classes with blank in the code, forcibly expanding the original 12 classes to 13. Corresponding to the very bottom of the model architecture, which is the NN dot linear output layer shown on the screen, we set the output dimension to non-classes plus 1. This extra neural serves as a dedicated blank output channel to learn uncertainty. When the model lacks confidence, it bases all its probability on this channel to remain silent. Next page. We set the temporal window to 128 frames and the grace period tau to 32 frames, meaning the model is forced to output blank for the first 0.64 seconds. So how how do we teach the model to remain blank for the initial 0.64 seconds? We had to rely on our custom data processing pipeline. Look at the line build a brand labels function on the screen. We set the window size to 128 and the grace period to 32. In this line, Y for non-classes, we use a brute force array slicing approach to force the ground truth labels for the first 32 frames of this 128 frames sequence to become the blank class, which is value 12. Through this teacher forcing training method, the model is compelled to memorize this 32 frames rule of silence. Okay, next page.
Wait a second. So because you could have achieved the same with the loss, right? So you chose to, I wonder which one is more complex, right? Whether a change in the data set or a change in the loss function, right? You understand my point, right? You could have also imposed this one here on the loss function.
Changing the loss function is more complex.
Okay, I believe you. I believe you. I'm not going to question what you said. Go ahead.
Okay, so next page. Okay, so here is the F1 paradox. At first glance, our overall accuracy is at 93%. Even if we ignore the blank class, it's still 91%. However, our macro F1 score dropped to 0.575. If you look at the confusion matrix, the reason becomes obvious. The model is highly accurate on the 6 basic long duration activities like walking and sitting. However, it is completely blind to the 6 postural transitions like standing into sitting. Because these transitions happen so fast and the samples are incredibly imbalanced, the model simply gives up on them. Since macro F1 treats all classes equally, our score tanks. This shows that accuracy alone is a misleading metric here.
Wait a second, let me think. So you say that activity 5 and 6 are sitting and standing, right? These are the two activities that you said. And you said that it's imbalanced because it doesn't happen so often, of course. Of course. There is a lot of class imbalance. Very nice. Yeah, so because it's the first time that I give this data set as an exercise. So I'm learning with you guys. Oh, nice. Of course.
Okay, next page. Okay.
Give me a second. Because you have 2 seconds window and you're capturing standing and sitting. And then the model is staying silent for 1/4 of the time. So the grace period, how much is the grace period in seconds? Repeat to me.
0.32.
0.32
sorry,
seconds.
64.
0.64 seconds. Okay. Very nice. Go ahead.
Okay. Took a look on this slide. Moving on to the blank detection performance, the model achieved a nearly 99% blank detection rate, meaning it successfully learned our grace period rule. However, we noticed that interesting information artifacts because our data set is pre-segmented into 2.56-second windows. Our current code forces the first 0.64 seconds of every single window to be blank. In the real world, continuous data stream, this will cause a wearable device to artifactually lose its memory every
Wait,
2.5.
Give me a second to parse this. So you said that you chop down the windows, right? Using a deterministic rule. Then you have a 50% overlap, right? And then you say, come again. And then what is happening there? Can you repeat that part?
Our data set is pre-segmented into 2.56-second windows.
Yeah.
Our current code forces the first 0.64 seconds of every single window to be blank.
Yeah.
Yes, this in the real-world continuous data stream, this will cause the wearable device to artificially lose its memory every 2.5 seconds. This highlights the trade-off of the grace period. If we make tau longer, we get fewer false declarations, but our detection delay increases. If we make it too short, the model guesses prematurely.
Correct.
Okay, next page.
No, just a second. Wait. Let me still stay there. I'm still thinking. Nice. I didn't think about this. Nice. So let me see the figure. What is the figure for here? You're just showing me that there is no overfitting, right? That's why you put the training and validation loss, correct?
Yes.
Okay. Losses cross center. Go. Okay. Go ahead. Very nice. Go ahead.
Okay. Next page. So, to the fundamental constraint here is causality. Because we remove the bidirectional layers, the model cannot smooth out its predictions using future context. This lack of future context is the primary reason our F1 score cannot match the offline model. But this is a necessary engineering trade-off. We chose protect practicality over absolute performance, while we sacrifice the ability to dictate split-second transitions. We successfully build a low latency, causally valid model that could actually be deployed on the real-time wearable device. Okay. Next page. Following up on the F1 paradox we just discussed, we further broke down the F1 scores for each class. As you can see in this bar chart, the performance isn't just average, it is an extreme by model distribution. Our model performs almost flawlessly on classes 0 through 5. Basic activities like walking and sitting, with F1 scores mostly above 0.9. However, for postural transitions in classes 6 through 11, the scores plummet below 0.5. From an engineering perspective, this tells us that the overall lower macro F1 is heavily dragged down by minority instantaneous movements. In the practical context of a wearable device, being able to accurately track primary long-duration activities already delivers massive deployment value.
So do you remember what is activity 10, 11? What are these extreme ones? Do you remember what's the activity?
So I had to check my code.
Yeah, just wondering, right? Because you said the 5 and 6 are sitting and standing. So I just wonder what is 10 and 11 that is so fast that you cannot detect it, yeah?
Okay,
要切吗？还是
等我一下。
Let me ask you then, do you wear any wearable device? Do you have any wearable?
No.
You don't have a smartwatch, you don't have a
I don't have.
band. Do you feel like buying one now that you that you saw how it works? No, no, because for example, just to tell you that this is a problem. For example, for the Garmin devices, right? They have an accident detection. So the watch, if there is a very high spike in the accelerometer, will send out an alarm because it thinks that you got run over, right? But of course, 90% of the time, the model makes a mistake. But it's this ROC kind of discussion, right? You want the model to not miss the real accident at the cost of detecting 90% of the activity, which is a false detection of an accident, right? So it's this is why the discussion on the F1 score makes a lot of sense, yeah? Because maybe activity 11 is being run over by a car, right? And so of course you're happy to have an F1 score and still keep the activity because detecting that activity has a lot of positive consequences. Yeah.
Okay.
Nice.
Okay. level 10 and level 11 is uh, 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 is stand to line and line to stand in the standard HAP mapping.
Okay. So that's why, right? Because basically there is no sitting in between, right? So when you go to bed, you just jump and you lie flat, right? And when you wake up from bed, you roll over and you stand right away, right?
Yeah, you're right. Okay, so uh,
Yes, yes, yes.
next page.
Yes.
Following up, okay, next
So
page.
my jokes always lie flat, right? Nobody laughs at my joke. God damn it. Go ahead.
Next, we conducted a very interesting validation experiment. We didn't retrain the model. Instead, we took the predictions generated from our original model training with a tau of 32 and evaluated them against ground truth labels with varying grace period lengths. Looking at this line chart, when our test standard aligns exactly at 32 frames, both the overall accuracy and blank detection hit a perfect peak. If we stress the ground truth expectation to 64 frames, blank detection is cut in half to 50%. This strongly proves that our causal GRU isn't peeking into the future. It honestly memorized and rigidly executed the temporal rule that it must remain silent for exactly the first 0.64 seconds. Okay.
Very nice. That's a good thing. Yeah. That's a smart thing to do. Yeah. Very nice.
Next page.
It's nice. Nice.
Okay, so let's look at the predictions on the timeline. This is very similar to observing a step response in control systems. Instead of just looking at one lucky sample, we plotted multiple consecutive test windows here in die 6, 0, 1, and 2. The orange line is the ground truth, and the blue line is the model's frame-by-frame prediction. Notice the incredible consistency across all these plots. In every single instance for exactly the first 32 frames, the blue line perfectly locked onto class 12. The blank class, there is no jitter or premature guessing. The very moment the grace period is up, it is instantly and accurately snaps to the correct class, which is class 4 in these examples. By stacking these examples, we prove that our model's online detection mechanism is highly robust and deterministic. It strictly and consistently prefers to stay silent rather than issuing a false alarm when the temporal evidence is insufficient. Okay,
Very nice.
next page. Okay, so uh, let's address the first question regarding the optimal grace period tau. Our empirical sweep clearly shows that 32 frames or about 0.64 seconds is a sweet spot. If we make tau too short, like 0 or 8 frames, the model is forced to classify before the sensor signal stabilizes,
Exactly.
causing overall accuracy to drop to 68% due to high false alarms. On the other hand, if we make a tau too long, like 64 frames, the model actually beats our ground truth. It starts predicting the true activity prematurely, causing black detection to plummet to 50%. Therefore, 32 frames is mathematically the optimal threshold for our dataset structure.
So, but this one here, you did it with the dataset with the already preset zero labels, right? Is that
Yes.
correct? Okay.
Okay, so next page. Question 2 asks whether the online detector can match the offline classifier. The short answer is yes on overall accuracy, but no on macro F1. Both models achieved 93% overall accuracy. The online model maintains high performance on steady state activities like walking or lying down because past history is enough to capture these patterns. However, it completely loses age during transitional boundaries without future context to smooth out the signal. The causal network struggles to pinpoint split-second postural shifts, which explains the drop in macro F1 to 0.975. Okay, so next page. Okay, for
Yeah, well, okay.
question
Yeah.
3, how often does the model make false declarations, and how long does it stay blank? Thanks to our training recipe, the false declaration rate within the gray zone is under 1%, as shown by our 99.2% blank detection score. The model spends exactly 25% of its time in the blank state, which is a direct reflection of our padding. 32 frames are out of the 128 frames window. Furthermore, early detection is highly asymmetric. Cyclic or static activities like walking or laying down are incredibly easy to detect right after the grace period. Hitting F1 scores is near 1.0. However, transient activities like sitting to standing are impossible to catch early because they finish before the model even exits its blank state.
Exactly.
Okay, next page. Finally, question 4 looks at how architecture impacts delay and blank duration. If we compare a GRU against a temporal convolutional network or TCN, it comes down to architectural structure. From our earlier baseline experience, the GRU has a much lower processing latency of 0.27 milliseconds compared to the TCN's 1.02 milliseconds in an online deployment. TCN's causal deletions create a fixed rigid receptive field, giving it to the mathematically bounded detection delay. However, because its kernel sizes are static, the TCN can easily overfit to the fixed 32 frames blank length. GRU uses continuous hidden states, making it more flexible with shifting blank duration, so it carries a slight risk of hidden state drift over very long periods of silence.
Yeah, very good. Very good, very good. Very good.
Okay, so thanks for
Thank you. Let's see if this works. Let's see this guy. Yeah, let's see this. I'm very curious about this. Go ahead, guys.
Hello. I will present a test for which focus on one-shot subject personalization for smartphone-based activity recognition. The main problem we want to sorry, just 我讲了翻译就好。The main problem we want to study is that a model trained on many users may not work equally well on new user, even if two people are performing the same activity, such as working or sitting down. Their motion pattern can still be different. For example, one person may work faster, another person may move more slowly, and their form precision may also be slightly different. So the goal of the test is to test whether we can improve the model for new subject using only a very small number of labeled calibration examples. In our experiment, we use 30 subjects, 12 activity classes, and different collaboration size from 0 shot to 10 shots per classes. The key question is, can lightweight personalization improve performance without changing the goal model architecture? Okay, next page.
Okay, let's see how we do. Yeah.
This slide shows the overall experiment. design, we use a lift one subject out protocol. This means that each subject is treated as a new on-scene or user once. For each round, we hold out one subject for testing, and we train the global model using all other subjects.
Mm-hmm.
The global model is a GRU-based sequence classifier. The input window length is 128 samples, which corresponds to 2.56 seconds because the sensor sample breadth is 50 hertz. We use 50% overlapping and the predict horizon is 0, meaning the model predict the current activity from the observed windows. After the global model is trained, we first evaluate it directly on the holdout subject. This is a zero-shot baseline.
Yep.
Because no personalization is applied. Then we sample a small calibration set from the holdout subject.
Okay.
We test different calibration size, 1, 2, 5, and 10 level windows per class. To make sure evaluate fair, we make sure that the calibration window and the test window do not overlap temporarily. Because the window recall the start time and its length, so I can do it in the code. So finally, each personalization method is evaluated on the remaining test window and is compared with the zero-shot baseline on the same test split. Okay, next page.
And then wait. And then you
Okay.
repeat. So my question is this, right? How do you average the performance there? You repeat the training for multiple holdout subjects then? Is that how you do it?
Sorry, again?
How do you evaluate this approach? How do you average the performance of this approach? Then you repeat the training for multiple different holdout subjects then?
How to average the approach?
Let me tell you this, right? So holdout is one. All the other
Yes.
subjects are in the train of the global GRU, right? So you obtain 1 point of performance, okay? Then what do you do after that? Do you average the performance by letting out user 2, training the global GRU, and repeating the process for a different holdout subject and average the performance? Or you always only have 1 point for one holdout subject?
Sorry. Can you type some keywords? I can't understand.
Let me tell you this. So the results that you give me are always for a fixed choice of hold down subject. Is that correct? Yes or no?
Fixed subject. I fix one subject hold down.
And then, the results are always for that one subject being left out, correct?
Being what?
Left out.
Oh, left out. Yeah, left out. Yes.
Got it.
That's not in training pipelines. It's
No,
just
but it's always the same guy, right? It's always the same guy. Okay, go ahead.
okay. And then next page. In this experiment, we compare 3 lightweight personalization methods plus the zero-shot baseline. The first method is zero-shot. In this case, we directly use the global model without any update. This allows us to make sure how well the model generalizes to a new subject. The second method is subject-specific normalization. Here we recompute the mean and standardized deviation for each sensor channel using only the calibration data from the new subject. Because the global model input is normalized, is divided by is sub mean and divided by STD. So I change the mean and STD only the calibration data. Then we normalize the test data using this subject-specific statistic. This method did not update any model weights. Its main risk is that when there are very few calibration samples, the estimated statistics may be noise. Okay, the third method is prototype classifier. We use the trend GRU encoder to extract the embedding from calibration window. Then for each activity class, we compute an average embedding as the class prototype. During testing, each test sample is assigned to the nearest prototype. This method is simple, but it may perform poorly on difficult or overlapping classes. The fourth method is linear head adaptation. In this method, we freeze the encode and fine-tune only the final linear classification layer using calibration data. This keeps the model lightweight and avoids modifying the global architecture. Okay.
Very nice. Very nice. Okay, go ahead.
Okay, next slide. This slide shows the few-shot performance curve based on Micro F1. The most important observation is that performance generally improves when more calibration examples are available. The best result is achieved by 10 shots linear head adaptation with a macro F1 score about 0.886. Subject specified normalization also performs well at 10 shots, reaching a macro F1 score about 0.885. This means that normalization can become useful when enough calibration data is available. The match tension. Okay. No. Previous slide. Sorry.
Okay. Sorry.
The match 10 shots 0 10 shot 0 shot baseline has a.
Is it 10 shot or 0 shot? Which one is it? It's a joke. Go ahead. Go ahead. The 0 shot, 10 shot. I got it. Go ahead. Yeah.
Okay. Has a macro F1 score about 0.64. Compared with its baseline, both linear head adaptation and subject-specific normalization shows improvement. However, the prototype classifier remains low in the score. This suggests that although prototype classification is simple, it may not handle difficult activity classes as well as Stern classifier head.
Yeah, we saw it before. I think that's too where they were doing all the clustering, right? So we knew that we saw there that there was not much information in this prototype stuff. Yeah.
Yeah.
Go ahead. Very nice. Go ahead.
Okay. There's notable point that the 0 shot one in the figure has one more point, right? At the leftmost. That's because only 0 shot can use 0 calibration example. Other require at least one calibration example. So that's why the figure seems like so. Okay. Next page. This slide compare the improvement over the 0 shot baseline using matched test split. This comparison is important because different shot setting remove the different calibration windows from the test set. So we should not compare all the 0 shot numbers directly across different shot setting. Instead, for each shot setting, we compare the personalized method with the 0 shot baseline evaluated on the same remaining test windows. The results show that linear head adaptation gives the most consistent positive improvements. For one-shot calibration, linear head adaptation improved the score about 0.0089. And for different shots, just show on the table. Okay. This means that one-shot personalization can help, but effect is not always large. The improvement becomes more reliable when we have 5 or 10 calibration windows per class. Subject normalization also become competitive at 10 shots, but it's less stable when very small calibration set, because it's statistics, so less data is just not enough. Okay. Okay, next page. This slide shows that personalization does not help every subject equally.
That was my question at the beginning. This was my question at the beginning, right? Because you see here, you repeat the experiment for all the different subjects. This is what I was asking.
Yeah. Some subjects benefit more from personalization, while the other remain difficult. For example, subject 12 show a strong improvement for linear head adaptation. This means that for this subject, the global encoders already provide useful features, and only the final classifier boundary need to adjust it. However, subjects such as 10 and 14 remain difficult under one-shot calibration.
But these guys here, we saw them before as well, right? Because we saw them before that when we did the clustering in task 2, those two guys, they ended up in two different clusters. So they were the outliers, right? So this is very consistent with the results before. Yeah, very nice, very nice.
Yes, yeah.
Go ahead. Very nice, very nice.
This may happen because one level window per class is too small to represent the subject's full motion pattern. Some activity, especially transition, may have larger variance and may require more examples. This result suggests that we should not only look at the average score, we should also examine the performance at the subject level, because real user may behave very differently. The practical implication is that pure one-shot personalization may not always be reliable in this data set. We are using at least 5 to 10 calibration window per class get more stable result. Okay, that's my part.
Let me ask you something. Do you wear a wearable? Do you have a wearable, like a watch or a band?
No, I don't have one.
Do anybody in your family wear one? Your papa, your mom, your brother?
No, there's no one wear that.
Yeah, very nice. Yeah, well, I wonder what those two guys, what they were doing with the device. Thank you very much, guys. It's very nice.
But I remember a member in our group used to wear, but it doesn't wear it now, but it used to wear it for
running, for health, for what? For what?
Hongchen, right here.
Okay, so you're calling him out by name. Yeah, go ahead. Let's ask him.
But it doesn't answer me.
He doesn't want to stand out. Yeah.
All right. Okay. So,
yeah, a lot of very nice. Very nice presentation, guys. Just a lot of things that I was thinking, right? So, for example, historically, right, women wear much less watches than men. But for example, I was just checking, like for wearables, the adoption of wearables is higher in women than in men. I didn't expect that. So I was just wondering, when we see these clusters, what type of things we're doing, right? Because maybe mostly we're like athletes or like amateur athletes, so they want to record their activities. So I was just wondering. Yeah, I was just wondering, because I think most of them will be very active people. And the people that wear smart watches, I think they are health enthusiasts and sport enthusiasts. So yeah, just wondering about the data. Okay, thank you very much, guys. Very good presentation. So let's take a break of like 5 minutes, because I need to go to a toilet. We've been sitting down for an hour and a half or something. So okay, I'll see you back in 5 minutes. Okay, guys, go drink, go walk a little bit, and then we do the next group. Okay, group bigger in the meanwhile. Ciao, ciao. Okay, guys, let's do group B. Can you tell me if we have a movie review tonight? Today? Okay, I think there is no movie review. Maybe. Go ahead, group B, please come talk to me. Oh, everybody left. Group B. Group B left. Group B. Group B. Group B. Group B. We don't have anybody from Group B? Let's see what the admin said. Group C. Okay, Group C, go ahead, please. Group C. There's nobody around today. What's going on? Group C, can you talk to me?
Okay. I'll share a screen.
Yes, let me check what is happening to Group C. Do we have a Group C, right? We have a Group C.
Yeah, we are Group C. We're Group C.
Sorry, we have Group B. Do we have a Group Group B?
Not sure.
Okay, maybe with the. I don't know because you guys formed the groups. I see. Got it. Oh, there is no author today. The author is not in the call. Why did the author didn't join? Okay, let me add the author. Sorry, guys. Why didn't the author join? I am recording, but we do not have the author. Thank you for reminding me. Okay, go ahead.
Show
Whenever
the
you're.
slide.
Yeah, sure.
Is it okay?
Just give me a
Okay,
second.
so
No, the author is there. The author is there. Okay, the author is in the meeting. Eh? Let me check.
okay, so I'll go through the data setup, and so before we look at the charts, I'll explain the preliminary setup. We use a UCI data set which contains continuous smartphone sensor data. Then the most challenging part of the setup was the raw accelerometer and gyroscope signal with the exact start and end time provided in the label text labels file. And so we cut this continuous signal into fixed length segments, and we call it windows, and normalize the data so our model can learn effectively. And we can look at the top left chart, which is a sample window signal. So we can think of this as a snapshot of exact what our neural network sees. The specific window represents the workdown activity. So you can see on the x-axis, the window exactly at 128 steps. So with about like 2.56 seconds, and the y-axis shows the normalized amplitude. So we can successfully combine all 6 channels for 3 acceleration and 3 for gyroscope. And next we move on the top right. We have a data set split. Yeah, we can to make sure our model evaluation is fair and we prevent data leakage. So we strictly split the data by subjects, not just by random picking data points. We allocate like 70%, so about 9,000 to subject to the training set, and 10% to validation, 20% to test, as a bar chart shows. This, yeah, and then.
So this is raw samples, so it's Windows. This is raw samples, right?
Yeah.
Okay.
And so then we see the bottom chart shows a fast distribution in a training set. So this is a very important finding for our next step, we can clearly see the massive difference between the first 6 basic activities and the last 6. So the basic activities have well over 1,000 sample each, and while the transition have like barely 100. So this severe class imbalance tells us that the model might struggle to identify the transition movement later. They'll cause a like bias. So because of this, we have to use a micro F1 score instead of simple accuracy to evaluate our model. So and then we go to task 1.
Okay, so for task 1, and this is the temporal window and sampling trade-offs. Next page. So before comparing like different window lengths and prediction horizons, missing data conditions, I first trade like the baseline GRU model as the reference model. So for this, I use FX20 and a learning rate of 0.001. So here I set the window size to 128 samples. So since this sample rate in the state of this data is 50 Hertz, so 128 divided by 50, which is 2.56 seconds. So this means that model observes 2.56 seconds of smartphone sensor data before making a prediction. So here you can see like the baseline results. The validation accuracy is 0.9128, and the validation macro F1 is 0.8. Next slide, please. So here, this slide analyzes the baseline model in more detail. So in the previous slides, we know that the baseline GRU achieves good overall performance. So the test accuracy is like 85% and test macro F1 of 74. So I want to know which activity classes are classified like well and which classes are difficult. So I use a confusion matrix, and you can see that from the confusion matrix, some models perform very well on several basic activities, like flying in had very strong performance with a recall of 0.99 and an F1 score of 0.97. And also walk down also performs very well. So this means that models can recognize stable or repeated motions activities quite well. So, but you can see that the model struggles more with postural transition activities, like stand to sit, sit stand, these things. So for example, lie to stands has an F1 score of 0.5, and stand to sit has the F1 score of 0.55. So you can see that these scores are much lower than the basic activities. So maybe this explains why the overall test accuracy is really high, but the test mark level is lower.
Excellent.
So you can see that the model performs well on common or stable activities, but the transition classes are more difficult for them to see. Yep. So you can see there are also some clear confusion patterns, like walk-in is sometimes confused with walk-up. About 21% of the true walk-in samples are predicted as walk-up. So sitting is sometimes confused with standing too. So with about 21% of true sitting samples predicted as standing. So this makes sense because like sitting and standing are both relatively static posters. So the sensor signal can be similar.
I think there's also many ways in which can be one can be the transition between standing and sitting, you know.
Yeah.
Also sitting in line, there are many different gradations of this. Go ahead.
Okay, next. So here we're going to discuss about the effect of different window lengths on the activity of performance. So here I test 0.5 seconds, 1 second is 2.56 seconds, 5 seconds, and 10 seconds of window. So since the sampling rate is also 50 Hertz, so correspond to 25, 50, 128, 250, and 500. So a longer window means that the model can observe like a longer period of sensor signals before making a prediction. So here you can see from the summary table, you can see that the overall test performance actually improves as the window length increases. So I think that is because that for us, I use the familiar setup of the strides to 64. So all of them is 64. So which means that their windows have the same numbers of the windows. Yeah. So For windows that have 10 seconds, which is longer, means I can see more things. So maybe this is why they have higher accuracies.
Correct.
Yep.
So this is what they discussed, the difference with the previous group, right? The previous group, they have this adaptive stride, right? But this one here, but now you have the same number of windows, right? So the learning instances are the same as the window length changes. Yeah. Go ahead.
Next slide. So here the heat map gives a more detailed. So you can see that one clear observation is that basic repeatedly activities such as walking, walk up, and walk down, so really perform really well with short windows. But so when the window length is up to 10, they also have really good accuracies. So this is probably because these activities just contain strong periodic motion patterns. So this is not hard to understand, but you can see that line also performs really well, saying around to 0.797 to 0.98. And some interesting improvement happens like in postural transition activities. You can see like sitting to lie improves from 0.4 at 0.5 seconds to like 0.81 at 10 seconds.
Well, yeah, let me slow down a second. Let me absorb this. Because you inverted the order, right, on the y-axis, so I have to now recalibrate.
Yep, you can see like all these transitions moves all increase their Markov F1. So for me, I think that the reason is that these transition activities are not defined by like a single instance. So for longer times, you can see more things. So in the window too short, the model don't see a small part of the transition. Yep. So this is like what I found here.
Just a second. Let me think about this. You don't go fast. What happens with the standing, right? For the standing, it goes down for 1 second and then it goes up again, right? Because that's not just noise, because the difference is substantial there, right? Do you have a theory there of what happens, for example, for sitting and standing, that there is this dip and then it goes up again?
I think that maybe when the standings, maybe the window just captured some of them after the new moves, so they just find it. This is not standing. Maybe they have like some swingings of their arms or what. So maybe they just think that this is another move. But if it's up to 2.56 seconds, it's long enough to let them know that, oh, this is standing, this is it.
Yeah. And that one, I was just wondering about the 0.5 seconds. Yeah, very good. Okay, I like your hypothesis. Okay, go ahead.
Yep, exactly. So here's the prediction horizon experiment. So here I set the horizons to 0, 0.5, 1, and 2. So you can see that from the summary table, you can see that the overall performance decreases as the prediction horizon becomes longer. So you can think that at horizon 0 seconds, the test accuracy is about 0.84, and the test marker is about 0.7. And at horizon 0.5, you can see that the performance is still very close, like with a test Markov F1 of about 0.7. So this means that maybe short-term predictions within 0.2 seconds is still possible for us to do. But however, when you see the horizon increase to 1 second, the test Markov F1 dropped to about 0.6. And when it increases to 2 seconds, it further drops to about 0.51. So this shows that prediction further into the future is really difficult for these classifications and activities.
Yeah, I would like to see if how is the per class performance, right? Because of course sitting it's a much longer period, right? So maybe the accuracy drop on the specific label is not so drastic. Go ahead.
Next slide, please. So here is also a heat map.
Perfect. That's the one I wanted to see. Let me look at it. That's the one that I wanted to see. Yeah.
So to sum up, you can see that line stays very high across all horizons. Walk up, stand up, walk down also remains relatively strong. So this like because these items usually last for several seconds. But you can see that postural transition classes are much more sensitive. So
excellent.
Reasons that transition are short D and temporarily. Yeah, so this results make sense from a motion perspective. Yep. So you can see from the down here the plot, the activity sensitivity to prediction horizons. You can see all these transition activities have more sensitivity to these to particularize these changes. Next slide.
Excellent. Very good. Very good.
Next slide, please. Thank you. So here we discuss about some subsampling and missing data experiments.
Okay. Okay.
So I simulated several missing data conditions and evaluate how much model performance drops. So the first group of figures shows examples of clear and corrupted sensor windows. You can
Okay.
see that
Clear and
the
corrupted.
window is labeled as standing. This is a standing sensor window. So you can see that all the six sensor channels are like smooth and stable. So this is set to be a standing. And you can see that the first corrupt example is a random point dropout with probability 0.3. So this means that
Which one is it? Which one is it? The second line. Okay.
first one,
Go ahead.
yeah.
Yeah.
So this means that around 30% of the individual sensor values are randomly set to 0. So there are many points missing, but you can still see some kind of temporal patterns. And the second corrupted example is block dropout. So in this case, the continuous segment of the signal is set to 0. So you can see compared to the random point dropout, this removes a continuous piece. And for the third is the accelerometer dropout. So yeah, here all three accelerometer channels are removed, and the fourth is the gyroscope dropout. Next slide. So here are some summary tables. You can see under the clean test conditions, the model achieves a test accuracy of 0.95. But there are some things to see. Yeah, you can see that when the dropout probability is increased to 0.3, the mark left on drops, which says that random missing data damage the temporal signals and reduce like classification performance. And as for blackout, you can see that the performance depends on the length of the missing segments. So with block dropouts, length is 10, the mark F1 is like 0.7, so which is only a small drop. But when the block length increased to 20, you can see that it drops more. So this suggests that moving a longer continuous segments really makes different things. So there are some most important results, which is the comparison between accelerometer and gyroscope. You can see that when the accelerometer drops out, it causes a large performance drop. So this maybe means that the model depends heavily on accelerometer informations. As for the gyroscope dropout, you can see it also hurts, but drops smaller. So maybe this shows that gyroscope information is useful, but for rotation and transition related movement. So it's not as critical as accelerometer information in this experiment.
Yeah, let me think a second, right? Because this was on the wrist, right? The device was on the wrist, right? Yeah. On the wrist, you have all orientations, yeah. But of course, probably, yeah. Okay, because this is absolute. Okay, nice. Okay, good, very nice, very nice. Okay.
So here the heat map shows some interesting findings. Is that when accelerometer drops is applied, you can see almost all activity classes collapses. Like for example, walking drops from 0.95 to 0, and lying also drops to 0, standing drops also to 0. So this strongly suggested that accelerometer channels are essential for recognizing both static posters and dynamic movements. And you can see under gyroscope dropouts, the model performs like better than accelerometer. But you can see the walking drops from 0.95 to 0.35, which means that they can still see some things, but not all. So, but you can see that all like sit to stand and stand to lie drop to nearly 0. So this suggests that like gyroscope data helps distinguish posture transitions and rotation movements, even though accelerometer data carries more overall information.
And of course, the lying one is the best one for the accelerometer, right? So it's.
Yeah. Next slide, please.
Okay, hello everyone. Today I will present task 2 of our deep learning challenge, which is subject embedding and clustering. So in this task, do you hear me?
Yeah.
Okay. In this task, we explore different subjects who move similarly according to a neural network, also have similar activity pattern. And we do this by comparing sensor-derived embedding with label-derived embedding. So we can go next slide. This is a task overview. So it's centered around the research question, do subjects who move similarly according to the neural network also have activity pattern? And our approach consists of 3 steps. First, we extract the subject embedding from two different sources. Then we cluster subject using both embedding types, and then we compare the clustering result to assessed agreement. So our goal here is to validate that the model learn meaningfully behavior and not just memorize the training data. So let's go to next slide, the architecture. So this is heart of our approach. We have two different pipeline that runs in parallel. So on the left, we have the sensor-derived embedding, and here how it's work. We start with a raw sensor window, which is 128 time stepped of 6-channel EMU data. And these windows are fed into our training GRU encoder. This is the same that we saw in the task one. And the GRU output 64-dimensional embedding for each window. And this embedding captured the learned movement pattern. And next, we pull those embedding for each subject. We average the embedding separately for each activity of 12 plus. So we get 12 average of vector per subject. And finally, we concatenate these 12 vector into one single subject representation, and thus give us a 768 dimension, which is 64 times 12. So this is for the first pipeline, and then the next one is the
Go ahead.
okay, is the label derived embedding. So we start with the activity label here, and then we from that label we compute then handcrafted features, which are time fraction, average duration, and etc. And then this give us in total we have 26 feature, which we normalize using standard scaling. So we end up with two different representation of the same 30 subject. One come from that neural network, and other from simple statistic. So yeah, now question is, will this create like the cluster subject will create the same cluster or different? So let's go to next slide, the clustering process. So this is our method. We first test multiple value K2, 3, 4, 5, 6. And our goal here is to find which is like the best clustering group to use. So then in the second step, we use for them a quality cluster quality using the silhouette scores. And this metric range from -1 to +1, and we try to aim for the best value. And yes, third step is we select the best value, and then we compare this clustering using agreement metrics. So we have the ARI. This is the metric that measure how similar two clusters are, and it also range from -1 to +1, and 1 mean that is perfect score, and 0 mean that they're completely independent. And we have the normalized mutual information, NMI, who measure how much information one clustering provide about the other. And it's a similar range. We try to aim for 1 if we want a similarity. So let's go to next slide. This is our result. So as we can see, for the sensor derived embedding, we see that the best score is for K equal 5. So it's not significantly higher than K2, but if you want, in that case, it's a little bit better. So we selected this one. And for the label of for the labeled embedding, it's really clearly we have that for 2 it's better, for K2 is better. So our optimal configuration is 5 and 2. So yeah, let's go to next slide. So here are clustering characteristic. So here we can see that cluster 1 is there is a pattern where we have 3 outliers, which is 0, 2, and 4 for this cluster. And we have two groups that form for we have a standing group and a lying group. And in that case, we still those outlier are maybe not wrong value. Maybe they try to sell something important that don't happen often. So in that case, it's not wrong. But for the label derived, we see two clear group of formations. So we have the walking group and standing group. So yes, that's what our result finds. So let's watch them visually in the next slide. Sorry. Okay. Yeah. First, we have to figure out if
It's
what
really
if it's really my opinion or there is really some number that says that those two are not similar. So yes, the numbers here are low, so there's maybe no correlation in between the group. We find like they don't influence each other, and we can just see that they try to capture different type of information. So the sensor derived embedding capture movement dynamically, so how people move, and yeah, the other one is try to capture something different. So yeah, let's go to next slide. So here we can see for the UMAP of the sensor derived, we clearly can see like also two groups, two massive groups, and we also notice some outliers.
outliers. Yeah. So
And for
0
the-
and 2 were the outliers, right? In the left, 0 and 2, right?
Yes.
Okay.
We can see those. I think there's third one, but I don't see it.
Yeah, it was 6 or something. Yeah, because you just didn't plot it, I think, right? Because you had. Oh no, you're right. You're right. Should
And-
be 1 and 3. What is 4? I think we don't see 4 because I saw it. There's 0, 0, 2, and 4. Yeah.
Yeah, I
those
should
are
have
the-
choose better color, but
yeah, it's, you have to squint a little bit, but I can see. Yeah, go ahead.
and for the label derived unbundling, we can see two good groups. So separation is much clean, and we see better boundary between them. So yeah, let's go to the next one. Next slide. This is just to visualize the clustering quality. So why we choose K5, and for the sensor and for the label why we choose K2. So and also next to it is to see like how much like they're similar and how much they like influence each other. So we can see again that they're not really connected. So yeah, next slide. And yeah, this is just summary of what I said since beginning. So it's okay. Yeah, that's it for the task.
But did you see that the clustering in the two groups was coherent between the two methods? I didn't see the number. Can you show me the number again? I missed it somehow. Yeah. So how many? Yeah. What is the consistency between the two clusters? That was the previous slide. No.
Yeah,
What was it?
the previous slide.
Can we go back one, guys? Okay. Let's go.
It's true that we can see that K2 in both cases, it was really pointing to 2.
Right.
So I agree that there is a consistency.
Okay, good. Okay, go ahead.
So yeah, next slide, and I'm finished. So next slide.
Good. Very good.
Next slide.
There is no slide. There is no next slide. What happened? Task 3. Okay, good. Who's gonna tell me about task 3?
You. So next we're going to talk about task 3, and in this task we'll first talk about the concept of grace period, which means how in this task, and to prevent like bad prediction during the activity transitions, we introduce a blank state which we will class 0 to following each transition set, and target within the grace period are relabeled to 0, and so it forces the model to gather more evidence before committing to a label. And we evaluated 0.0 second, 0.5 second, and 1 second. And so in this slide, we train 20 apples for each matrix, and we can see that the macro F1 converge at 0.71, and it achieves stability across all conditions after about 15 apples. And for the false declaration rate progression, the 1 second when tau equals 1 second, it achieves lowest error, which about 7.5%. And for while the green line, which is when tau equals 0 second, it suffers about 11.5%. And for the blank time cost, the 1 second requires about 30% blank time, and which is 6% increase over 0 second. And for the delay fluctuation, it is highly sensitive to event level sampling and yes.
Detection
So
delay. Detection delay.
yes.
Because you have a
Oh,
target one. Okay.
Yes.
So they have a certain, I see, in seconds.
Yes. So for me, I would choose tau equals 0.5 seconds for the grace period, since it can strike a balance between the false declaration rate and the blank time progression. Okay, so next slide, please. Okay, so here is the main detection delay by this class.
So
And
the model really learns the dynamic of the activities, right? That's very interesting. Wow.
yes, so for the left, it was the GRU, and the right is the TEN, the another TCN, the
TCN,
another
temporal convolutional network. Yeah.
Yes. So for in the picture, we can see for postural transition, like sit to stand or lie to sit, and they driven, since they have like huge changes in the picture, so they can detect very fast. But for walking or sitting, standing, it just like it doesn't change a lot. So I think the model have to make like look at the data for more seconds, so it can know about like what state it was at. Like yes. And
So look at the difference in lying, right? Look at the difference of the two model in lying, right? Why does one guy decides right away when you're lying and the other model is like, oh no, let's chill. You know, it's a curious difference between the two models, right?
right. So and so between the two, like the difference of two architect is the like this for I think the most we can see that the seats to stand, like for the TCN it was you have like no bars, and for the GRU it was 1.28 second. And I think because TCN didn't see the history data, so it missed to it can like see the differences of sit to stand.
Understood.
Okay, and next slide.
Okay, so in text 4, we're talking about one-shot subject personalization. Yes, next page. This method involves training a global GRU module on all but one subject. We then test this module on a held-out subject in a zero-shot manner. No adaptation is applied, and then attempt lightweight personalization using only a few labeled calibration windows.
Calibration, yeah.
Okay, next page. So first, we observe that the global module's performance drops when faced with unseen subjects, although the gap between global and zero-shot performance is modest. The modest drop confirms that subject variant matters justify the necessity and usefulness of personalization methods.
Necessity, not necessity. Necessity.
Yes, necessity.
When if I say something like this, don't say sorry, okay? Because we're not. Yeah, we're just discussing English language, okay? Go ahead.
Okay, next page. We evaluate several lightweight personalization techniques against the zero-shot method. First, linear head adaptation shows the highest gains and remains close to the zero-shot method. And then subject normalization starts lower than the linear head, but follows the same upward trend. It ultimately provides small but stable gains over the zero-shot performance. Prototype-based classification starts with same score as subject normalization, but exhibits a lower increasing rate. Critically, the prototype method is consistently below the zero-shot baseline. Overall, all methods shows increased performance as the number of shots per class grew. The linear head is the only method that clearly tracks the zero-shot baseline, leading to the conclusion that while lightweight adaptation helps, not all methods are equally effective. Okay, next slide. This is the improvement for the three method.
This is very different from the previous class, right? From the previous group, right? The previous group showed substantial improvement, but you guys cannot, don't see any improvement. I wonder why. Yeah, go ahead. But you understand what I'm talking about, right? So this is the same figure as the other group, right? It's just that you guys show no improvement.
Yes.
But this is the GRU, right? Yeah, this is the GRU model. Yeah. Windows is 128. Yeah, go ahead.
So here you can see linear beats subject and prototype by 4% and 14% at 10 shots per class. So yes, next page. When examining class-wise recall at 10 shots, a significant challenge emerged. The module struggles to distinguish transitional activities from static activities. This suggests that transitional activities may require more data than static activities to be accurately personalized. Because personalization successfully closed the gap for sustained basic activities, but all methods fail on postural transitions regardless of calibration size, revealing a fundamental data scarcity problem rather than a module limitation.
Very good. Excellent.
Okay, next. So first question is, how large is the performance gap? And does personalization close this gap? So the gap is surprisingly small, only about 2.4% on average. More interestingly, subjects 4 and 5 actually score higher on zero shot than the global module.
meaning the global module already generalized well to some individuals. This suggests the GRU encoder learn reasonably general motion representations rather than overfitting to training subjects.
GRU.
Yes, GRU encoder.
Yeah. Go ahead.
Next question is, which personalization method performs best for one-shot or few-shot calibration? Is it constant across subjects and activities? So we can see that linear head adaptation consistently outperforms the other methods at all shot counts. It is the most consistent winner. So note that prototype classifier failed to reach 0.8 F1 score even at 10 shots, suggesting that nearest central in the embedding space is insufficient when the embedding space isn't tightly clustered per activity. Okay, next slide. How many calibration examples are required to achieve a given accuracy threshold? Basically, basic activities need very few examples because they are long, repetitive, and well separated in embedding space. Postural transitions needs many more examples and may never reliably personalized with only 10 shots.
Of course.
This is a fundamentally class imbalance problem that personalization alone can fully fix. Next, do subject profile vectors from text to help condition the module effectively. Text 2, subject profiles offer limited practical benefits for text 4 for 3 reasons. First is low interview agreement. Sensor embeddings and label embeddings group subject differently. A profile vector built from one view doesn't reliably predict how the module should shift for a new subject in the other view. Additionally, the classifier on a text-to profile would encode the wrong structure. Next is we cluster to begin with. The solver. I forgot how to pronounce
No,
this.
go slowly. So just try. I'll help you. Don't worry. I'm here to help you.
Silhouette scores of about 0.2.
Silhouette.
Yes.
Sorry. I was trying to guess, and then when I got it, I was just screaming.
I just asked Google to help me how to pronounce it. Yes. Scores about 0.2 indicate subjects don't form tight, well-separated groups in either view. Conditioning signal derived from noisy cluster assignments would add noise rather than useful personalization signal. And the final is the few-shot collaboration already provides direct subject significance signal. At 10 shots, linear head adaptation directly adapts to the actual new subject's data. A profile vector from text 2 is an indirect population level summary that adds detail on top of direct adaptation and risks overfitting when combined with given only about 120 collaboration windows. Okay, this is the end of our presentation.
Very good. Do you have a wearable? Does anybody in the group have a wearable?
I don't have one.
Are you a very sporty person?
No,
Do you like to run?
never.
Never. You've never done any running, any sport, anything. So if we attach the sensor to you, we'll just say sitting all the time. Very good,
For
guys.
me, it is.
Come again? What do you say?
For me, it is true.
Very good. Because I have to, I have two wearables. I have my watch and I have my Whoop, and I'm always recording stuff. Okay, guys, I think the other two groups we're doing next time are really, I always say the same thing, but it's very difficult for me to stay focused on what you guys are saying 100%. So do we have any movie review? Do we have any CAD? Can the student that show adding a CAD before, can you show me the CAD? So we do something different. We are not always talking about silhouette scores. Yeah, can you show me the CAD model that you were having? Or yeah, I think next time we're gonna have a movie review at least. Yeah, go ahead, guys. Tell me something interesting, and then something more interesting, and then we move forward. Can you show me the CAD model at least, please? And I'll post something funny in Slack. Let's see if you guys enjoy it. Hello. English spelling. I'll put it here. English spelling. Little joke. Okay, guys. Since nobody had anything to share today, unfortunately, the challenge 4 is very interesting, right? So challenge 4 is on BERT embeddings. So you can download BERT, which is, yeah, we haven't discussed word embeddings, but it's a topic that you can look into yourself. It's very, very interesting. It's partially related to this hidden feature of the RNN we discussed last time. As I said, at the end of next week, I shall, by the end of this week, I will provide the final challenge. Remember that you can form the groups as you want. You'll have a month and a half to do it. It is kind of boring, as I said, from my standard, but I think it's okay. I think it's an interesting topic. Hopefully you'll remember the topic if you forget about me. And otherwise, that's it for today, guys. Okay, I'll stop the recording now. We say goodbye to the people on YouTube. Remember to subscribe, like, and whatever. And we see each other in class next time when we're going to do the next two groups. Okay.